Now that we've addressed the limit definition for the derivative, now it's time to show you some of the rules here, the shortcuts. But before we do that, I want to make sure that we've addressed the different notation you're going to see. This is the one I used in class. I'm assuming that Mrs. Babcock and Mrs. Ware as well did. But be mindful that this is similar to the derivative. So it's similar to delta y over delta x, except we use the Roman d and the Roman d instead of the Greek d. I meant to write x. So with that said, you can also write the derivative as dy dx. Now think about this. Right here, this is your function. This is y, right? So sometimes you're going to see it written like this. And I'll explain in a minute, f of x. Sometimes you're going to see it written like this because it's like function notation. It allows you to see what the function is that you're going to be taking the derivative of. And this one is pretty useful. It's kind of just nice and consolidated. And if you think about it, if you put it over 1 and multiply them, you get your dy over dx again. So all of these notations are the same. And so if they ask you to evaluate one of the derivatives at a certain x value, let me just show you what that would look like. Let's say we're evaluating it at x equals 1. Well, then this would be, what is the first derivative when x equals 1? Don't forget, the first derivative is also known as the instantaneous rate of change. ROC, rate of change. Okay, whereas this one is the average rate of change over an interval. If we wanted to evaluate this one, well, Delta Math, they write it like this. They write it dy dx when x equals 1. But I want you to be familiar with this notation as well, because this is how we write it, and your textbook uses it as well. I want you to find the derivative of y when x equals 1. That would be the notation. But like I said, you'll see it like this in Delta Math. This last one I've seen a couple different ways. I've seen it this way. We're taking the derivative of this function with respect to x, and then evaluate it like this. I've also seen it written like this, because it's really df, the function, over dx, and then you evaluate it like that, similar to this. All right, let's get into some of the rules. And first up is the constant rule. Okay, this says that the derivative of a constant function is 0. That is, if c is a real number. And this is the notation. We're going to take the derivative of this function c, and the derivative of it equals 0. Think about what a constant function looks like. Let's say this right here is my constant function, and we'll call it y equals 3, also known as f of x equals 3. Well, you tell me, what's the slope of any straight line? I don't care if you pick these 2 points, or if you pick these 2 points, or if you pick these 2 points, you're always going to get a slope of 0. Ta-da, that makes sense. On to the next one. The next one is the name of our video, so I guess this one's pretty important. This is the power rule. If n is a rational number, then the function f of x, which looks like this, x sub n, maybe x squared or x to the third, it's telling you. Well then, in order to take the derivative of a function that looks like that, this is the process. Okay? What you do is you take the exponent. If it's a 2, you put it in front, and that's the exponent. And then what you do is you take whatever your original exponent was and you subtract 1 to it. Let's do an example before we finish the theorem, what it's saying there. So I have, let's do f of x equals x to the third. If you want to take the derivative of your function, well actually let me use the notation here. You want to take the derivative of x to the third with respect to x, it would look like this. You take your exponent and move it in front. It becomes your exponent, and then you take this exponent and you subtract 1 from it. And that becomes your new exponent. Okay? So that right there, the derivative function is 3x squared. Now, let's finish what it says here. For the function to be differentiable, so you can take the derivative at x equals 0, n must be a number such that n minus 1 is defined on the interval containing 0. Basically, just be mindful that if they're saying that if your x is 0, so if you have a 0 with a negative exponent, well, you might remember negative exponents put that value in the denominator. So if you end up with something that looks like this, well, that's not defined on the interval. So just be mindful of those scenarios. Now I'm going to clean up my screen here a little bit, but please be mindful that if you need to copy any of these rules down, well, pause the video. The beauty of a video. Let's get to the next one here. It's called the constant multiple rule. This one says that if we can take the derivative of f, if it's differentiable, and c is some real number like a constant, like 2, 3, 3/3, 3/4, 3, right? Then the constant times your function is also differentiable. Here's the notation. Let me show you an example. Say I have an f of x, and we call that 3x squared. Well, the derivative of f of x would look like this, right? They're saying just leave your constant, and what you do is you take the derivative of this piece, okay, of f, and this would look like this, 2x, and don't forget, you reduce the exponent by 1, so that becomes x to the first. And then at the end, we multiply this, and it becomes 6x, and that's your answer. And what does this last one have for us? Let's see what this one says. The sum and difference rules. All right, well, this states that the sum or difference of two differentiable functions, two functions you can take the derivative of, let's call them f and g, then they are also differentiable. All right, so again, it doesn't matter if you're adding or subtracting. Don't forget, subtracting is just adding a negative number. It's all really adding. So if I could take the derivative of f and g, then I can take the derivative of the sum of them, etc., for the difference. Let's do an example. Say I give you y equals 4x to the third plus x. And I ask you, well, now this is the sum of two of them, right? And, well, the derivative of y, oh, I forgot to put that in there too. If you're also going to see y and y prime. So why don't you add that to your notation? You're taking the derivative of a function. If you're calling it y, then it's y prime. And that would be this. Well, I have the 4, so this is my variable, so I'm going to do 3x squared plus, well, this one, the coefficient is really just a 1, so what you do is you take the 1 and you multiply there, and you get 1 times 1. And then when you reduce the exponent by 1, guess what you get? Well, that's a 0 as your exponent. Do you remember what that equals? Anything to the 0 power equals 1. Okay, anything. Doesn't matter if it's this. Please be mindful. So if that's the case, the derivative of y would be 12x squared plus 1. All right, example time. Y equals -4. Well, that is a constant function, right? And that is going to be dy dx, the derivative of y. I'm going to just switch up the notation so you get comfortable with it. Well, that is going to be 0. It's a constant. Now that we know the power rule, I just want to show you something here. You could think of this -4 as having an x to the 0 with it, right? Because this is nothing more than 1, so it doesn't change the value. Well, now that you know the power rule, what if you follow this rule, right? 0 times anything is 0, and I don't really care where the x is. 0 times anything is 0. How about another example? How about y equals 3x to the 4th minus 2x plus 1 over x. Okay, so let's introduce something new here now. The rule I said before says you take the coefficient, right, and you put it in front, you end up multiplying those two real numbers, and then you reduce the exponent by 1. So, well, let's do what we already talked about. The derivative of y, could also be written as y prime, would be 3, this becomes 4x to the third, -2, remember this is a 1, so this just becomes x to the 0. Now what do we do with this one? Well, let's just clean up these two terms, because I think you know this is going to be 12x to the third, and this is -2 times 1. Well, we didn't talk about fractions yet. It's not like you take the derivative of the top and the derivative of the bottom. That's not correct. We need to be able to rewrite this. Do you know that 1 over x is equivalent to x to the -1? You need to know that. If you have 1 over x to the third, that is equivalent to x to the -3. Okay, so please be mindful of that. So if that's the case, I could rewrite this term as x to the -1. And now we get to follow our rule, because what you do is you take your exponent and you move it in front. So I have a 1 times a -1 gives you -1. And then here's my base, my x, and I'm going to take this exponent and I have to reduce it by 1. So -1 is -2. So this right here is -x to the -2. Now, sometimes you will see the answer written as negative exponents. Sometimes you will see them rewritten with a positive exponent. So know that these two are mathematically equivalent. Okay? There you go. Let's focus on that negative exponent for another minute because it's going to pop up quite often. So let's do this one. I'm going to start with an f of x. I have f of x equals, how about 3 over x minus 5 over 2x to the fourth. All right, let's see how this one pans out. I want to take the derivative of f of x. Well, before I do that, I can't do it the way I'm looking at it. So what I'm going to do is I'm going to rewrite it. So before I write f prime of x, which is a different function, I'm still at f of x. I just want to rewrite it to help ourselves use the power rule. If you follow what I said up here, this is going to be, well, this is really 3 times 1 over x, right? So that just becomes 3x to the negative 1. And this right here is really just a 5 halves. 5 halves times 1 over x to the fourth. So I could rewrite that as 5 halves x to the negative 4. And now remember, this is still the f of x. Now it's time to take the derivative. F prime of x, you take this is the power rule, well, constant power rule. You multiply those and you get negative 3x to the negative 2. Don't forget, you reduce the exponent by 1. Here, I'm going to take a negative 4, and I'm going to multiply that. Let me rewrite it so you get, this is negative 5 halves times a negative 4. And then I have my base, and I reduce the exponent by 1, makes that negative 5. I just wanted to make sure you see what I'm doing here. So this one, now the x is the only thing with an exponent, with a negative exponent, so the negative 3 doesn't go downstairs, it's just the x squared. Here I have a 5, well here, let's multiply that out. Negative negative is positive. 5 times 4 is 20. And then over here is 2. So that's going to reduce down to a 10. So let me just erase that and write 10. And we have our x to the negative 5th, but like we just said, sometimes you're going to see them written with the negative exponents, but sometimes you're going to see them written like this. Plus, now the 10 over 1, it's just the x with the negative, so the 10 stays where it is, the x to the 5th goes downstairs. Let's throw in a radical now. What do you do for the derivative when you have a radical? Let's do a problem here. Say I give you y equals the square root of x to the third minus 2 over the cubed root of x. How about that? This will give you a nice flavor of how to handle these. Now, before we take the derivative, let's help ourselves. Okay, whatever is inside the radical there, well, you need to know that that's raised to the 1/2. There's another fact that, let me change the color here. If you're unaware of this, you need to be aware of this. If I give you the square root of x, well, think about it. This is a 2 and this is a 1, so the exponent is your numerator and the root is your denominator. If you follow that same pattern, say I gave you the 5th root of x to the third. This is how you would write it. Okay, so know that. Let's continue. So that's x to the third. Minus, now this right here, this is the same thing as a 2 times a 1 over the cubed root of x. So I'm going to leave my negative 2. How do I rewrite this? Well, let me go over here quick. So 1 over the cubed root of x, that is equivalent to x to the 1/3, if you follow what I just said here. Now that I have this x in the denominator, we can negate it and put it upstairs. So that is the same thing as x to the negative 1/3. I'm still not on my derivative yet. I just want to clean this one up. What do you do when you have an exponent raised to an exponent? You multiply them. That is x to the 3/2 minus a 2, x to the negative 1/3. Let's take the derivative. What is dy dx? The derivative of y with respect to x. Well, follow the pattern, 3/2. Now, you reduce this by 1. Remember, I'm going to call that 2 over 2 because we need a common denominator. That gives you a positive 1/2. Here, we take this, we multiply, positive. 2 times a third is 2/3. And don't forget, you reduce this exponent by 1, but since I'm dealing with a third as a denominator, let's call 1 3/3. Negative 1/3 minus 3/3 is negative 4/3. That's how it would look with negative exponents. Here is what it would look without negative exponents. There you go. Let's look at this blue f of x here. What can we do with this one? Well, we're going to learn something called the quotient rule soon, but we don't know it yet. And honestly, we don't need to know it. Watch what we can do here. I like this method. That's a common denominator, right? That's common to all of these terms up here. So we could rewrite it like this if we wanted to go back one step, if you will. Because when you add these different terms, the first thing you need is a common denominator. And once you have a common denominator, what you do is you leave the common denominator and then you add or subtract the tops. Yep, I forgot that's a +4, not a -4. So if you rewrite it like that, well, again, I'm not taking the derivative. All I'm doing is rewriting my f of x. Do you remember what to do here? You're dividing, so what you do is you subtract your exponents, and that's going to give you x to the first. There's a -3. Well, we don't have to do anything. Those are just going to cancel. And do you remember how to write this one? Because we don't have a division. There's no x upstairs. So it's 4x to the -2. That right there is a pretty darn easy derivative to take. Let's continue. The derivative of x. Constants become 0. You multiply this and you get -8. And don't forget, when you subtract 1, you get a -3. There is the derivative with a negative exponent. And here is the derivative without a negative exponent. Let's take a look at g of x now. G of x has the same concept where it's a common denominator. However, you notice the denominator is a radical. So many times what's helpful is you're going to change these, before you take the derivative, change them to fractional exponents. We talked about what to do here again. If that's a 2 and that's a 5, that is x to the 5/2 minus 2 to the x to the 1/2. All right. Now, with this, it's a little bit easier to see that the g of x with a common denominator, if you separate that common denominator, you're going to get this. And in this format, we can subtract our exponents. We have a common base. 5/2 minus 1/2 is 4/2. Well, 4/2 reduces to 2. That's convenient. Over here, this is a -2, and, well, we're going to just cancel those out, so it ends up being 1. So there is the g of x. We didn't take the derivative yet. Now, the derivative. G prime of x. Constants become 0. Okay, let's take the information we just learned, and now we're going to use that to find the equation of a tangent line to some curve at some x value. The curve that they mention here is the f of x or the g of x, whatever they give you. So let's start off by giving you an f of x. Our f of x will be -2x squared plus 5x plus 4. And you may remember from your geometry days, oops, that's a terrible one. It's an upside down parabola. I don't know where it is on the xy axis, but I know it's a -x squared. And somewhere on here, I'm going to have a random point where the x is 2. I don't know the y value yet. I just know that x is 2. And on that point, that coordinate, there's going to be a tangent line. And our goal is to find the equation of that tangent line. First, we need to know what's the y value. Because when you find the equation of a straight line, does this ring a bell? This is your point-slope form of the equation. There's two things we need, a point on the line and a slope of the line. Right now, let's find the y value. When x is 2, the f of 2 is your y value. So this is going to give you 2 squared plus 5 times 2. I think, there we go. So what is that? 4, -8, -8, 10. That's 14. I'm sorry, that's 6. So now we know that our xy coordinate is 2, 6. 2, 6. Now we can fill in a lot of this right here, the equation of the tangent line. We now know it's y minus our y value. We know it's x minus our x value. We just need to find the slope of the tangent line. The slope of the tangent line is your first derivative. Let me just copy the formula, the equation down here. -2x squared. Just so you can see the power rule in action. The derivative of f of x, -4x plus 5, constants become 0. If I want to know what the slope of the tangent line is when x is 2, you plug in a 2. And you're going to get the slope of the tangent line is -3. That negative 3 is what we need right here. That is the equation of the tangent line in point-slope form. I'd like to go through one fairly quickly here just to at least give you another example. So we're going to find the equation of a tangent line to the curve now at x equals 1. Our curve now this time is a g of x. Okay, so here's our g of x. And we need to know the y value, because don't forget, our goal is to find the equation of a line, so we have to plug it into the point-slope form, and we need to know the x and the y. So when x is 1, your g of x is 2 minus 1, it's 1. All right, so that means that you have the coordinate 1, comma 1. When x is 1, y is 1. So now I can plug in this, y minus 1, x minus 1, but we need to know the slope of the tangent line. Well, the slope of the tangent line is the first derivative. If you're starting off with g of x equals 2x squared minus 1, the derivative of g of x is going to be 4x. If you want to know the slope of the tangent line when x is 1, you're going to do this and tell me it's 4. The slope of the tangent line is 4. There's the equation of the tangent line.